Hello and welcome to this video on limit comparison test. One of the prior knowledge that you will need for this video is a direct comparison test, and some of the knowledge that will help you with some of the problems are the nth term, geometric series, telescoping series, p-series, and the integral test. The direct series test is fantastic, but sometimes it gets challenging to figure out the convergence of some of the more challenging polynomial fractions. In this example here, we got 1 over n cubed minus 2n squared plus 8n minus 1 as our sequence, and we want to see if this series converges. An integral test is one of our options, but it is very time consuming to take the integration of this as a function. We could use the comparison test. We can take the highest degree, 1 over n cubed, and compare our series with 1 over n cubed. But is our series bigger, is it smaller, or is it bigger in certain domain and smaller in others? This is sometimes a difficult question to answer, and therefore we're going to use a different method, the limit comparison test. We can use the limit comparison test when we have two series which are both positive. Let's figure out what will happen if we were to take the limit of n approaching to infinity of an over bn, and if that reached a value L, where L is a real number which is bigger than 0. If we were to do this graphically, we will see two different sequences which are approaching a finite value as n approaches infinity, and if we were to divide those finite values, we would reach that L value, which is our limit. We know that the L value is bigger than 0, so we can actually plot it on a number line. Now we can choose a ratio between 0 and 1 and add and subtract it from L and plot it in the number line. Note that the L value here is the limit of n approaching infinity of an over bn, and the region in between 1 over 2 and 3 over 2L are an over bn for some n value. You can see in the diagram that if an was the red and bn was the blue, at the very beginning n is equal to 1, the ratio between them is approximately 2. And as n approaches infinity, the ratio gets much smaller, so let's say approximately 1.1. So 3 over 2 times 1.1 is approximately 1.65, and since we know that the ratio is getting smaller and smaller, we know that for some n value, in this case we'll call that n value capital N, the ratio between an over bn will fall somewhere within that pink region, which is 1 over 2L to 3 over 2L. Now we're going to put this into writing. We know that an over bn is between 1 over 2 and 3 over 2L for some n value. Now we can multiply everything by bn, and we can see that 1 over 2L times bn is smaller or equal to an, which is smaller or equal to 3 over 2L times bn for some n value larger or equal to n. And this would mean that if we were to take the sum of the two series from n is equal to n to infinity, that would mean that 1 over 2 times the limit times the sum of bn from n to infinity is smaller or equal to the sum of the series a of n from n to infinity, which is smaller or equal to 3 over 2 times the limit value multiplied by the sum of the series of bn from n to infinity. Now this is very nice because we know that for the sum of the series from n is equal to 1 to n is equal to n, it will definitely be something that's convergent. What we don't know is whether things are convergent from n is equal to n is equal to infinity. And this would imply that if the sum of this series from n to infinity, if it converges, that means the whole series converges, and if it diverges, that means the whole series diverges. This further means that if the series bn converges, that means an will also converge because of the direct comparison test. If 3 over 2 times L times B series bn converges, that means 1 over 2 times L times the series will also converge because they're just a ratio of each other. One is 3 times as big as the other. In the same way, we can say by the direct comparison test, if bn diverges, since an is larger than 1 over 2 times the limit times that sum, it will also diverge. Let's summarize the concepts here. If we have two sequences a and b which are both positive, if we were to take the limit of n approaching infinity of a over b, and if we obtain a value which is a real value larger than 0, then the series a and b will either both converge or both diverge. Now let's look at an example, the example that we did at the very beginning of the lesson. The divergence or convergence of 1 over n cubed minus 2n squared plus 8n minus 1. Okay, a tip. If you want, you can use your sequence B as the known, so that's the series that you know converges or diverges, and your sequence A as the one that you don't know, so that's the one in the problem. So we are going to let the sequence A be 1 over n cubed minus 2n squared plus 8n minus 1, and the sequence B to be 1 over n cubed. Now we know that 1 over n cubed converges due to the p-series test with a p-value of 3, which is larger than 1. So we can take the limit of n approaching infinity of a over b, and that's equal to the limit of n approaching infinity of our first fraction multiplied by the reciprocal of the second fraction. And if we were to divide n cubed as shown, we would get 1 as our final answer. Since the limit is equal to 1, which is not equal to 0, therefore we know that our series converges by the limit comparison test. I will leave you with some practice questions to try out. They start easy and they get more challenging. For the very last one, you can try comparing it with 1 over n, and that is your hints.